Hi, everyone. Welcome to this episode of Context Swaps with Karthik. I'm Vivek Khandelwal, your host, and today we have with us Karthik Soman. Hi, Karthik.
Hey, hi Vivek. Hi
I
Joshua.
got
Hey,
like,
hey. We also have Joshua, my fellow co-host. Hey, Joshua, how's it going?
yeah, Vivek.
All good. All good. Excited about chatting with Karthik today. Karthik, quickly for for the audience, I know you don the hat of a data science expert at SAP, and you have done some extremely interesting work during your research stint at UCSF, where you have done some groundbreaking work on the spoke and developed the KG RAG, and you also been a speaker at the conference and stuff like that. But that's all like that's the LinkedIn resume of yours, right? I would love to understand, a bit more about Karthik Soman, the the knowledge graph enthusiast. What's your story? How did you end up doing what you're doing right now? Walk us through your journey, please.
Yeah, sure. Thank you for having me and really excited to be here. So you know what, Vivek, like looking back at my journey that when you mentioned that it really has been an exciting ride and honestly each step it felt like a natural progression rather than a leap, I would say. So I think I would start from my PhD journey itself so that that gives a complete picture. So it all started with a curiosity about the brain. So I did my PhD in IIT Madras. And my area of work was in computational neuroscience. So I was essentially trying to understand how exactly the brain processes information using mathematical models and algorithms to understand how neurons communicate with each other. And what that really taught me at its core was how to think about complex networks and how to extract meaningful insights from highly complex data. So my next step was actually into the world of knowledge networks, specifically biomedical knowledge graphs or biomedical knowledge networks at University of California in San Francisco, at UCSF, as you said. And if you think about it, there is actually a beautiful connection there because the brain itself is a network, and it's precisely that interconnected structure that gives the brain its power, right? So similarly, knowledge networks give connected data its power or its wisdom, I would say. So at UCSF, I got to combine my computational background with machine learning and graph neural networks and apply all of that to real clinical problems. Things like early detection of Parkinson's disease, understanding multiple sclerosis through multiomics data, microbiome data, and building knowledge graphs that connect millions of biomedical concepts together. And that's actually where I invented KG RAG, a knowledge graph based retrieval augmented generation. Essentially, it is a framework that combines knowledge graphs with LLMs or large language models to make AI more accurate, more trustworthy, and more grounded in real world knowledge. So instead of the LLM relying purely on what it learned during the pre-training stage, so KGRAG extracts a relevant subgraph and provide that as a precise structured context to the model. But the number I'm most proud of is that KGRAG got adopted across UCSF campus-wide deployment. So real researchers and clinicians or biomedical researchers and clinicians across the campus are able to capitalize on that particular work. So that particular work, particularly at the intersection of knowledge graphs and generative AI, is exactly what brought me to SAP. So, as Andrew Ng famously said, AI is a new electricity. It's domain agnostic. So I worked on biomedical domain, completely shifted that domain, but those principles and those algorithms, that still remains the same. The same challenges I was solving in biomedicine, that is building AI systems that are not just powerful, but also reliable, explainable, and grounded in real knowledge. Those are exactly the same challenges enterprises face every single day. So in a way, I never really switched fields. I just kept following the same question. That is, how do you build intelligent systems that actually work in the real world? And that question led me here.
Thank you so much. It's a very interesting, what seems like unorthodox on the outside or unconventional on the outside. And I want to go back to something what you said in your introduction is that you worked on neuroscience, trying to understand how the human brain processes complex information. how the network works. A lot of people very casually draw the analogy that the human brain, that the LLMs are an excellent representation of the human brain and are as intelligent as they can be, so on and so forth. There's obviously clear evidence that they miss uh, a big part of what is what is conventionally referred to as system one and system two. System one being the part of the brain that allows you to do excellent pattern matching and so on, and system two, which is slower, allows you to think, process, recall, apply rules and logic, and so on. LLMs historically have missed the system, or standalone LLM based applications, the system to sort of an approach, right? I'm curious, what's your read on that? So because you mentioned your work involving doing deep dive into how the brain consumes information and trying to understand that, and you obviously extensively worked on LLMs, machine learning, and so on, right? In your opinion, what's the missing piece there right now, or are we already there, right?
Yeah, I mean, that's fantastic question, Vivek. Actually, I have come across with similar discussions on other people also, something on these same lines. But what I have felt is that we are just comparing apples and oranges. LLMs and human brain, they are like two different things. So the name itself, right? It's artificial intelligence. It's not the human intelligence which we see in the brain. So there are connections at a high level, I would say. Like if you look into the history of AI itself, if you, I mean, in when people start to think about perceptron kind of network and all, they were trying to emulate what brain was doing. So they know that the intelligence is there within those connections, within that network. So they were trying to emulate that using adaptive learning rules and all. So basically LLMs, which we call them, they are neural networks itself, right? So if you really dissect that anatomy of the LLM, it really works because of those, those parameters or the weight connections between these artificial neurons, which we call, and the entire system is trained on back propagation kind of algorithms. But now when you take human brain over here on the other side, the major difference between these two things is that brain is a dynamical system. So brain is not something which it's not. I mean, there are predictive coding inside the brain, but it's not like a next token prediction kind of algorithm. It's like brain is much more nuanced and much more enriched. As you said, there are like multiple cognitive centers within the brain, and each cognitive center itself is a dynamical system, and how they interconnect to each other. And you can look at brain at multiple levels. People have studied brain at single neuron level, where they have observed and published very interesting dynamics. For example, Hodgkin-Huxley model and all. It's a biophysical, a very highly detailed model of neuron. But when you go to a bit more high level, you can visualize brain at oscillations level. Like each state of mind has an oscillation associated with it. So how these oscillations are related and how it processes the cognitive information. Now then there are people who look at functional level, using MRI studies and all those things. So that's population coding of the brain. So at multiple levels you can study the brain, and one thing for sure across all these studies, the one consensus is that brain is a dynamic system. But on the other end, LLMs, the basic unit of LLM itself is a static neuron. It can be a nonlinear ReLU neuron or whatever high-ended nonlinearity that we bring into. So, but the amazing nature of LLMs is that because of that huge representation capacity that it has, because of that parameter space, it's able to do or extract out a huge number of patterns from these humongous billions or trillions tokens of data, and it is able to generalize on that. But comparing it with human brain, I think that's way oversimplification. We are just oversimplifying, and we are not giving enough credits for our human brain for that. Yeah, so that's my take. And I think there was a similar question that was asked to Andre Karpathy also during one of the podcasts, and his response was also very much on the same lines. I mean, these are two different things. Like LLMs or AI, in one, they are mathematical functions. right? So you stack one mathematical function on top of the other, and there is a beautiful theorem called universal approximation theorem. Like, given enough representation capacity to a neural network, it can approximate if any function with, of course, with some criteria. So these are mathematical functions which we are talking about, and they do amazing jobs, which is fantastic. But comparing it with a human brain, there are a lot of other nuances which we are missing over there. So yeah, so that would be my take.
Thanks. I think it's very important to remind people that these are two distinct concepts. Comparing them is not factually correct, but it's a very good range bait on the internet. So do go ahead and compare it if you just want likes and comments. Yeah. Right. Karthik, one thing which I wanted to go back to also is you've been using graphs before language models were formally introduced and were popular and so on and so forth, right? What changed since the introduction of LLMs in terms of leveraging graphs as a technology? And like also help us understand, where is it where you think you've leveraged KG over, let's say, a conventional machine learning model, right? Where do you find them more, let's say, powerful or more applicable as compared to conventional machine learning?
Yeah, sure. I think I would take the second question first over here, because we are talking about pre-chat GPT era, like pre-LLM era. And that's actually a great example too. And because so I can specifically, I mean, rather than talking in a very general sense, I can specifically pinpoint on one specific project that I undertook at UCSF. And that was a moment that really shaped how I think about AI in high stakes domains. So the project, it was early detection of Parkinson's disease using electronic health records. So the question that we asked was, so Parkinson's, it's a neurodegenerative disease, right? So the neurons within the brain starts to degenerate and the cognitive decline happens. But the thing is, you start to diagnose Parkinson's disease only when the disease gets aggravated, when these motor symptoms and all start to be very start to show, like you start to show the signs of tremor and all those things. But the fact is that this degeneration starts way before. So, but you are not able to detect that. So the question that we asked to ourselves is that, like, can we leverage the power of AI diagnose Parkinson's disease even before a clinician diagnoses that? Because a clinician diagnoses a Parkinson's disease when these symptoms start to showcase very evidently. So, SIF has like a very large database of electronic health records. So we try to capitalize that rich gold mine to answer this question. And the standard machine learning approach would take a patient's history, run it through a model, and give you a risk score. Something like, this patient has 77% probability of developing Parkinson's in future. It's useful, but it's a black box. Because as a clinician, end of the day, these models will be deployed in a clinical workflow, right? So as a clinician, you are left asking, okay, I understand that you are giving me a risk score, but why? So that question, that question of that reason or transparency is what's lacking in the typical ML-based models. So what the knowledge graph gave us was fundamentally different. So what we did, especially for this project, is that we enriched the patient's electronic health record data with a biomedical knowledge graph called Spoke, so that essentially this graph connected millions of biomedical concepts. So we leveraged these connections, these biomedical connections or biological connections in this graph in order to enrich the electronic health record data of the patient. So essentially, we connected these clinical nodes to actual biological relationships such as genes, proteins, symptoms, pathways, so on and so forth. And one of the most striking things we found was that, like, once this was enriched, once this clinical data was enriched with this additional biomedical information from the graph, we were able to see things that was absolutely not present in the clinical data. So one example is that a gene which encodes an olfactory receptor turned out to be a highly relevant feature for identifying patients even 5 years before their actual Parkinson's diagnosis. that connects to something real in the biology, because we collaborated this with a Parkinson specialist at UCSF. So we happen to know that loss of smell is one of the earliest non-prodromal symptoms of Parkinson's, often showing up years before any motor symptoms appear. So the graph didn't know this patient reported smell issues. It inferred a biological pathway connection that pointed toward the same underlying mechanism. And here is the part that really stuck with me, because as I mentioned, we actually had a movement disorder specialist. He independently reviewed some of these patient charts. And there was a case where our knowledge graph model correctly flagged a patient as prodromal PD. So prodromal in the sense before that pre-diagnosis phase, prodromal PD, and the clinician missed it. It's not because the clinician wasn't skilled, but because the relevant signal it was scattered across biological connections. And that's not something a human can manually trace across a chart in real time. So I would say that's not a better number. That's actually a different kind of answer. One really that points to an actual mechanism, one a clinician can, I would say, question, investigate, and learn from. So, and that distinction is what convinced me, knowledge graphs, they are not just a nice to have feature for enhancing accuracy. They were essentially, they are actually essential for building AI that clinicians could actually reason with, not just take orders from. So yeah, so that's one specific moment I think I can share here.
Karthik, that's like a really cool example that you shared. Just wanted to understand. So, how did you go about this with rules already encoded about the relationship between like drugs or genes or something like that? Or was this more of some kind of, the data being present and then finding a pattern? And like, how did you go about that? If you can explain to the viewers as well.
Yeah, sure. Great question, Joshua. So as I said, we capitalized on a knowledge graph called Spoke. So I think I didn't give enough introduction on Spoke on that end. So Spoke is a heterogeneous biomedical knowledge graph that we developed at UCSF in Bransony lab. So it has like at that time while I was working, it had like close to 40 million biomedical nodes, such as diseases, genes, proteins, symptoms, organisms, etc. And it had more than 70 million relationships between these nodes. And the way in which we curated this graph is by integrating publicly available databases, more than 40 databases. To give you an example, UniProt gives information about proteins. Then there is gene ontology. Then there is disease ontology. Then there is NCBI taxonomy. So like this, we have integrated 40 plus databases into one single graph database, so that all these disconnected or disparate sources gets integrated into one single platform. So now you can actually traverse on this graph, right? So if you can start from a gene and you can all the way, okay, what's the protein that's encoded by this gene? And this protein is associated with what disease? And what compound treats this disease? And does this compound regulates this gene? So you get the entire mechanistic information from the graph. So this is the substrate. This is what we used in order to enrich the clinical data. And when I say enriching clinical data, what I meant is that, let's say a patient comes to a doctor and reports that he or she has symptom 1, symptom 2, symptom 3, and they have been on medication 1, medication 2, medication 3, and they have lab test results 1, 2, 3. So they have like 9 clinical variables here: symptoms, medications, and lab test. And these 9 variables could be some entities in the graph, some clinical entities in the graph. So we connect those entities, so these reported clinical variables to the graph, and then we run a graph algorithm on top of it, exploring what are the other relationships. From this entry point, what are the other nodes or what are the other biological relationships that are existing in this graph? So, and we create a vectorial representation for the patient, which is driven by clinical data, end of the day, but it is enriched by the knowledge graph. So you get more information. So there is no way that you get information about genes and proteins from a typical clinical data, but you can get that from a knowledge graph by integrating it in this way. So that's exactly what I meant by patient data enrichment. And with this, vectorial representation, or with this representation of, or you can call it as a patient signature, enriched patient signature, then you can train any ML model. Then actually in the paper, we compared it with, train the same ML model with raw clinical features and train this ML model with these enhanced patient signatures from the knowledge graph. And from a performance, from an accuracy, or from a performance metric itself, there was like a huge difference. But on top of that accuracy, or on top of that performance metric, that explainability factor is what I really need to hinge on. Because even if you give a clinician a model which is 99% accurate, it is not of much use to him or her unless that model explains why it is predicting this particular patient has this particular disease. Otherwise, it would be like a black box model, which they will take with a pinch of salt. But instead of that, it says, I think this particular patient has a Parkinson's disease because I happen to see these genes or proteins which are reported as biomarkers for Parkinson's disease. Even though that was not present in the clinical data, knowledge graph was able to pick that because of this enhancement or enrichment.
Thanks. Yeah. So like what was striking to me when you were describing that was you are actually using two modes of what you see in the graph world today. You're using one mode, which is, like strictly typification, entities, entity types, the classes, different types of classes, different types of relationships. And this is what we usually see in the RDF world.
Mm-hmm.
And you can do that in a property graph as well. But then you're also flipping it to run data science on top of, these connections, because there are some things that are not yet codified as rules in, let's say, an RDF system or whatever, right? Where you're very clearly saying A causes B. You don't know that yet. And so you're actually flipping and you're using graphs in a different way. I mean, the other side of it, which is the data science part of it. And both have kind of been fused together. And you also mentioned vectorizing that. So you have like a neural and a symbolic side coming together. So yeah, that's pretty cool. Thanks for explaining that for the viewers there. I'm sure they'll be like very excited to hear about this.
Absolutely. Yeah, that's a fantastic thing that you mentioned, Joshua, that culmination of symbolic AI and that neural network approach or the machine learning approach, combining together them, that really makes a big difference over there, especially in, as I mentioned, in this high stakes or accuracy sensitive space like biomedicine. Yeah. You
Yeah.
summarized it well.
Yeah.
Yeah. Awesome.
Awesome. No, thanks for that, Karthik. Now, Karthik, you spoke about how in the healthcare clinical domain, there were these very beautifully curated, created ontologies that existed, which you could leverage pretty much out of the box for most part. Now, given that you have now moved to a much larger organization, right? What is the reality there in terms of what reality do you see when you work with large enterprises, when you work on seemingly a lot more messier data?
Mm-hmm.
What's the ground reality that you're able to see now,
Yeah.
especially in terms of their readiness to actually, either having ontologies in house themselves or the lack of it, or
Even the
often
awareness
at
of
times even the awareness of it, that like what's an ontology once again, like, yeah.
Sure. Yeah. So yeah, that's a very important and interesting question. So I think I would take this very systematically as a response. Maybe I will just reiterate some things which I mentioned before regarding the spoke. Then I will come into this enterprise context. So there will be like a stark contrast that people can appreciate it. So with spoke, as I mentioned before, I can say that we were building that graph on decades of community curated ontologies, like say, for example, disease ontology, Unipro, Campbell, gene ontology, NCBA taxonomy, to name a few. So there are like 40 plus such databases which we have integrated. So these are vocabularies that thousands of researchers have refined and maintained over years with real rigor behind them. So which means every gene will have a stable identifier. Every disease will have a consistent name across sources. So that foundation still took real research work to integrate and maintain but at least the underlying vocabulary already existed and was trustworthy. So when you move into the enterprise world, that data harmonization aspect becomes a fundamentally different challenge. And to be clear, that's not a governance gap unique to any one company, because enterprise organizations, they generally invest heavily in data standardization for structured data, such as where there is a table, where there's a defined schema, defined fields. But free-form text, such as documents or wikis or ticket information, those things live in a different world, because natural language just doesn't carry the same built-in discipline that a database schema does. So the natural first instinct is to do what you would normally do with an unstructured text. That is named entity recognition, entity resolution, entity harmonization, relation extraction, essentially harmonize everything into a clean ontology. But people have dedicated, there are people who have dedicated their life into building ontology and all. So that approach could hit a ceiling in terms of pragmaticity. So not because the underlying data is disorganized, but because freeform enterprise text simply doesn't have the terminological consistency that decades of biomedical literature curation gives you. So the same concept can be phrased 10 different ways across 10 different documents. And there is no equivalent of a stable cross-referenced identifier to anchor it to it. So a different approach, so worth considering, is to either, as I mentioned, either you can go over the typical conventional way, or the other approach is to lean on the topology that is already existing within the documents themselves, or the structure of the document. If you just to give an example, if you look into Wikidata, right, or wiki knowledge bases, that knowledge base itself has a knowledge landscape, such as how documents cross-reference each other, what's the structure of the document within itself. So rather than imposing an ontology on top of unstructured text, you could essentially build a graph out of the documents on architecture. And for structured data, like tables, databases, for such data, you can build the knowledge graph directly from the relationships already encoded in the data itself. And so if I just want to summarize that, I think so really what this teaches you is that ontologies, definitely, they are incredibly powerful when they exist. But in domains where the curation infrastructure, where that curation infrastructure is not available, maybe the structure of the data itself can serve as a starting point for graph-based reasoning. And it's not a replacement for a well-curated ontology. I would say it's a pragmatic path into graph-based reasoning when the alternative is waiting years to build one from scratch.
That one was like, how do we, so one is like you have structured and unstructured, and there are challenges there. But sometimes even in structured, if you look at the meaning of the column or the meaning of the table, and you might find a similar table somewhere else in the enterprise, or you might find similar names. How do enterprises deal with this, or how should they deal with this in order to control meaning in a very reliable way? Because it could be a completely different context when you use the same term somewhere else. So what are your thoughts on that?
Yeah. Yeah, so that's not a new problem, right? Because that's something which people have researched for years. So it falls under the category of entity resolution. So the same name Apple can mean a company, and also it can also mean a fruit, depending upon in which context you are using that. So that entity resolution, so there are like multiple methodologies which people have adopted to tackle that problem. But when it comes to enterprise scenario, I think the highlight word over here is the scalability aspect. So you can have tons of such tables and such kind of ambiguous keywords or words that may be scattered across these 1,000 different tables. So one thing, so I think I'm drawing this from one of the projects that we collaborated with NSF, National Science Foundation. So so that project is called Proto-OKN. OKN stands for Open Knowledge Network. So I think we can draw a lot of lessons from that particular project to this specific question that you asked, Joshua. So Proto-OKN, the idea of Proto-OKN was to integrate discrete or disparate knowledge bases into one single platform, a federated knowledge graph, essentially. So at the time while I was working at UCSF, so we collaborated with this project. It was like a multi-institution collaboration. So UCSF was part of that, and across US, like multiple institutions, but even outside US also have collaborated into that project. Oh, not outside US. Not outside US. That was a different project. Sorry. So within US, a lot of other institutions also collaborated. But the idea is this one. Okay, you integrate Spoke, you integrate other knowledge graphs, you integrate other database, may not be in a graph database, it could be like a structured typical SQL database, but end of the day everything comes into one single common data platform which has one schema, and all these data sources talk to each other in a federated fashion. And the very first thing that was done on that particular project was to have like a common language that these databases can talk to each other. I'm not mixing things here, but I just just like a knowledge graph, I'm connecting dots here. So I just wanted to bring up another initiative also along with this NSF. So NSF Proto-OKN is one project, and there was another initiative from a National Institute of Health and AH called Biomedical Translator project. It was undertaken by NCATS. So essentially, the problem was essentially the same, that is, integrate multiple disparate data sources, but this was mostly focused on biomedical domain. NSF was general. It can be anything. It can be legal data. It can be biomedical data, financial data. So for NCATS, what they did was they created a common language which these knowledge bases will talk to each other. It's called BioLink. So whatever you can define your own data modeling schema for your graph or whatever database that you're working on. But the minute when you bring that into this in this translator ecosystem, your database should speak this language, this BioLink language. So just like that, so Proto-OKN also has a very similar concept where these databases talk to each other in a similar language. So where I am heading towards with all these examples is that standardization part is the key thing first. That's a very first thing to do, especially at an enterprise scale level, because NSF or NCATS, we are talking about across country-wide collaboration. So that's also a highly scalable project, right? So whatever lessons or whatever measures that were taken as a consensus across multiple prolific researchers, so that carry a good weightage, so that can be translated into an enterprise context also. So you can have like multiple departments within an enterprise ecosystem with different tables. And as you rightly pointed out, Joshua, there could be ambiguity between the data terminologies, the way in which things are defined. But once you have a common language where you can integrate everything into that standardization pipeline, I'm not saying that's a trivial solution. That's something which will take time, but that's a necessary solution, because I see AI has three layers. Like, this data is the most foundational layer, and then there is application, and then there is model layer. So you can build all the nifty models, but it doesn't matter, because end of the day, if your foundation data layer is crappy, your model is going to be crappy, because your model is only as good as your data. So investing enough time, fund, and energy into this data standardization pipeline and building that that seamless integration of data from multiple modalities, that will have a ripple effect that will definitely reinforce the downstream AI models too.
So I think one part of this, what you're explaining, is like something like a data mesh for different, functions, even in the same enterprise. And, you would have like this common translation. It could be levels also. So it could be level 1, level 2, coming to a centralized, form. And the other part of this, when you were explaining, like, how enterprise deal with it. So one is like within an enterprise, you have this, translation across functions. How about kind of like hierarchically for the domain? Like let's say a finance domain, right?
Mhm.
Like we know that there is FIBO, right? And for legal, there's like LKIF. So like, how would you, walk an enterprise through, let's take finance, for example, FIBO, right? So would you recommend that domain ontology and then layer up to, obviously, because there's going to be, very specific nuances in that company. how would you, recommend that pyramid?
Yeah.
How would you nail that?
Yeah. So again, Joshua, I really want to stick on to the first principles here, because we don't want to reinvent from scratch. We can actually take all the principles that have been over here, which people have developed and has been proven to be very successful. Well, so take Spoke as an example. When you mention about different departments, right? You can think of this as different entity types within a graph. Let's take a department called gene department, a department called disease department, a department called organism department. All these are different departments, but just like in an organization, how different departments synergistically collaborate with each other, these individual departments, biomedical departments, will synergistically have a dynamic connections between them. So so now when it comes to the data modeling aspect, it's not like we are building one single ontology for the entire ecosystem, for the entire disease gene, everything. It's not like we are building one ontology. You have disease specific ontology, you have gene specific ontology, you have symptom specific ontology, you have organism specific ontology. And once you establish that semantic layer, then you go into the data integration process. So data modeling, data integration, these are two different pillars, strong pillars of this entire data pipeline. So I think we need to invest for individual domain. They have to build their own domain specific ontology, and once that is built, then we move forward with the integration process, because the integration becomes seamless when you have a defined ontology or defined vocabulary for each domain. Because when it comes to domain, you need to take care of those highly nuanced semantics of that particular domain, right? Just like how Apple can mean a whole lot of different things depending upon the context. So for that, domain specific nuances needs to be taken care of by this vocabulary or this ontology. So just restating what I mentioned before, this highly rigorous vocabularies like gene ontology or disease ontology, which Spoke capitalized in the data integration process. So drawing lessons from that in the enterprise ecosystem also, if each domain spent enough time to build their own vocabulary, then the data integration and all these federated data integration aspect, having one that data mesh kind of aspect that you mentioned, Joshua, that becomes pretty seamless.
Got it. Thanks. And is there something that you would recommend? So, a lot of times we've spoken to people that we expect to have ontologies, but maybe because they're different stakeholders, they're not aware of things. So, do you have some go-to ontology? So, biospace, yes, but when it comes to business,
Mhm.
what would you recommend as your, go to, like you said, don't reinvent the wheel. It's already
Yeah.
there out there. So do you have some, go-to ontologies for businesses that are simple for people to, get started with, and also they can kind of layer on top of that and add their own concepts?
Yeah, it's not that as straightforward as compared to highly curated biomedical ontologies, but I know that there exist some ontologies for, say, for example, for IT specific aspects. Honestly, I forgot the name of that ontology. I can look that up. But this is something which gives structured vocabulary for the IT operations. So if you want to build something, a knowledge graph for IT related aspects. So I think there are like two or three.
Like
Two,
SaaS companies and stuff like that
yes,
would be
yes,
good for them.
yes. So that would be one ontology that I would recommend. As I said, I'm sorry, I don't remember the name on top of
That's
my
okay.
head.
We can drop it in later.
Yes, yes. Yeah. For other departments, I'm not pretty sure, because, and that's the whole reason why personally I adopted um, an ontology free. I don't know if that's a controversial name to state, but something that captures on the document structure itself. There you don't require an ontology per se. Yeah, it's more of like I would like to call that as a loose KG approach. Like a single node is not an entity I mean, it's not like a highly defined, highly granular entity. A single node can be a paragraph. or it can be a list of cross references. But that's fine. I mean, you may not get that super high resolution in over there, but still you get that high level knowledge landscape, and that itself has proven to be highly invaluable, especially for this RAG context.
So what you're saying is, especially when it comes to unstructured, you schematize the document structure itself,
That's
and
right.
that becomes a great starting point
Yeah.
to mine things.
Yeah. So it's not just from a Gen AI perspective, even from a completely,
Even to model it, even to think about it, it would make sense to look at what kind of documents are
yes.
you dealing with in the first place.
Yeah. Right. So speaking to people, I have seen that you build a typical vector database based RAG approach. So what people asked, okay, yeah, it's answering the question, but it's not giving me the chain of provenance over there. I need to know how this document is related to other documents which we use in our day-to-day work life. So a vector database approach won't give you that, because in its essence, within vector database, data is disconnected. You're creating semantic embeddings, you're storing it. And of course, yeah, you can provide some metadata like parent-child relationship and all, but that would hit a ceiling. But that's where the knowledge graph can really help you over there, because you don't have to re-engineer anything over there. I mean, the topological connections is something knowledge graph gives you for free. So walking over that knowledge graph and capitalizing on that topology, that has been shown to be very invaluable. Stakeholders were pretty happy seeing not just the response accuracy, but also that explainability part, that chain of provenance. That was humongous when it comes to knowledge graph based approaches.
So I have a question here going back to your spoke.
Hmm.
Uh, y- uh, so here you're recommending like a kind of a pure KG RAG approach, right?
Hmm.
Is there any kind of a requirement or a scenario where you would say, just like in Spoke, you were analyzing via graph data science or graph neural nets, like some kind of business use case, then to go one step further, and it won't be like vectorizing text, but vectorizing the structure itself. Do you think there is any reason to do that, or that's overkill in an enterprise scenario?
Yeah. So that's a good question. So what I want to do here, Joshua, is that before getting into the brass tacks of this particular question, I just want to take a step back here, and I want to give a bit of a history, and then coming to this question. I mean, end of the day, you will see how these things are related. So when people talk about graph based reasoning, or why graph based reasoning is that actually the right thing to do for this particular data, they often treat this one as like a completely a brand new idea. But if you actually trace the research or the core concept itself, right, like using graph structures to represent knowledge and reason over them, it's decades old. So for example,
All of
if
computing, like everywhere you
yeah,
look, there's a graph.
exactly. I mean, it really starts with this Rose Quillian in the 1960s, where he published a paper, I think it's in 1967, where he modeled human knowledge as semantic networks, concepts as nodes, relationships as edges, and inference as literally walking across that graph. That's graph-based reasoning, and that is 60 years before LLMs even existed. Then in the 70s and 80s, people like Marvin Minsky and Brackman, they formalized this knowledge-based approach into, they call it as frame systems and conceptual graphs, where you could do actual logical inference over the structure. So we are talking about that RDF flavor here when it comes to 70s and 80s. But when it comes to 90s and 2000s, we get this semantic web stack like RDF, OWL, Sparkle, and large scale knowledge graphs like DBpedia, Freebase, etc. So these were genuinely being used for reasoning and question answering applications at scale. Then when it comes to 2010, so during 2010, 2011, 2012, let's call it as 2010s, then there was like a lot of papers were published on representation learning methods, like trans E, trans H, trans R, rotate E, node to vec, then graph neural networks like GCN, graph Sage, so on and so forth. So the point that I'm trying to make over here is that these are established research standards for using graphs in both predictive and reasoning tasks. So what LLMs actually changed is not the idea of using graphs for reasoning. That idea has been around for more than 60 years. What's new is that we now have models that can directly read and use graph structure as context in natural language, that too on the fly. So now coming back to the specific question on, okay, so graph has been over here for quite a while and people use that for reasoning and all. So do I need to use that for my application? So I just wanted to I just wanted to answer that in a quantitative fashion by citing the KGRAG paper which we published. So in KGRAG, there was one specific observation which we have mentioned it in the paper. That is, we observed like a significant improvement in the performance of question answering.
I think you said 71%.
71%. Exactly. So let me get into that number, that 71% number. So that number actually came from benchmarking on a data set called Biomix QA, which is essentially a data set that is curated by domain experts for this particular purpose. And we made it publicly available on Hugging Face, by the way. So this 71% improvement we observed applied specifically to Llama 2 model with 13 billion, 13 billion parameters, which is a smaller open source model. On that task, as I said, KGRAG gave like a 71% relative improvement. So, but when we ran the same framework on GPT 3.5 and GPT 4, we still saw improvement, but the margin was larger with Llama model. And that's actually a really important signal because GPT 4, at that time, this is in 2023, I'm saying. So GPT 4, I think, was the state of the art model. So GPT 4 already has a lot of biomedical knowledge baked into its parameters from pre-training. So for straightforward factual questions, a strong model with a standard vector RAG is often good enough for those simple scenarios that requires a single hop reasoning. But when it comes to complex questions that requires multi-hop reasoning, which requires chaining together 2 or 3 relationships that are not sitting next to each other in any single document, a knowledge graph would significantly help in this scenario. And this comes down to a fundamental difference in how the data is structured. As we discussed before, in a vector database, each chunk of text is essentially disconnected from the others. So you retrieve based on semantic similarity, but there's no explicit relationship between one chunk and the next. I mean, as mentioned before, you could assign some parent-child relationship there, but that would easily hit an upper ceiling. So a knowledge graph, on the other hand, encodes those relationships directly. So in terms of spoke terms, this gene interacts with this protein, which is implicated in this pathway, which is associated with this disease. So when a question requires walking across that chain, the graph already has the connective tissue built in, when vector search doesn't. So just to summarize, if your use case is mostly direct factual lookup, vector RAG plus a strong model will get you most of the way there. But the moment your questions require a complex level reasoning and multi-hop reasoning, or you are on a smaller, cheaper model where you can rely on parametric knowledge alone, that's exactly where a knowledge graph earns its value, both in terms of accuracy and also in the transparency, in the explainability factor, because you can actually trace the path the answer came from. So yeah, so that's my take.
So another point in this is that, see, like for the biomedical QA that you ran, that might have been publicly available. But if you're talking about a company's knowledge, that wouldn't be publicly available. So it would actually, if at all there was something in there, it could even directly oppose or hallucinate what is actually in, like privately in those documents that a company has. So, and if you think about the volume, the larger the volume is, and the smaller your neighborhood to search semantically, I mean, in comparison, with relative sizes, then you are actually like really compounding that problem because one, you don't have that knowledge in its parametric memory. You don't have it relatable via at least normal text embeddings because of the volume of it. You might also have another thing that we've seen is like a lot of like maybe dense concepts in one paragraph, let's say, if that is your chunk size or whatever that chunk sizes are increased now because the model context size increase as well. So it's basically like I think it's bigger in public data sets. Absolutely, I agree. Like wiki or like published QA data sets that would already be trained. Like that's what you immediately you publish. They're probably taking it and training it, right? I mean, New York Times articles and everything is like all covered there. So this is like nothing, right? It's in Hugging Face. They take it. But when it comes to like a enterprise, like a actual company's knowledge, I think the chances of it being present in a public data set is less, and therefore the chances of a hallucination occurring, and definitely like you said, the provenance, you will not get like perfect provenance. It might be the right answer, but you will not get provenance on that. So I think yeah, what you said really like resonates on that.
Yeah. Just one additional thing that I just wanted to add on top of what you said, Joshua. That's you are 100% right. And nowadays, if something is publicly available, yeah, it's kind of guaranteed that the next version of Claude or
Yeah.
GPT model or Gemini model, it may be in the parameters of that particular AI model. But there's a difference in making a data publicly available and getting out of insights from the data. So there is a concept in informatics called informatics pyramid. So just to give you an example, let's say a lab is conducting an experiment and they collect the raw data. So that is raw data. You can make it publicly available for other labs. It doesn't matter. That's the raw data. So that's the bottom
Baseline.
layer.
Yeah.
Yeah. Now you look into that data and you label the data. Oh, okay, this corresponds to this one. This corresponds to this particular label A, label B, label C. So now you transform that data into information. And then for each information which you have annotated or labeled, you draw connections. Oh, okay. So this is connected to this particular aspect. So you draw connections over there. So then that information gets transformed into knowledge. And once you have that at the knowledge level, you can get mechanistic insights by traversing over that connections. And that is called wisdom. So you see, you started with raw data to information, information to knowledge, knowledge to wisdom. This you won't get despite whether your data is publicly available or not. This is exactly what knowledge graph provides you. So when you're working on let's say a standard vector RAG approach, I would say you're mostly at that information level. You might have converted your data into information when you do the semantic embeddings. But that knowledge graph, that drawing connections, that's where you hit an upper ceiling, because how many top K will you retrieve from your vector search? And how do you know that's the right top K for you? Maybe for this complex question, you may have to retrieve 1,000 top K. I'm just making up some numbers here, but I'm saying you cannot say that a priori. So that's where a knowledge graph would pitch in and say and give you this organically. Yeah. So I just wanted to add that on top of what you said.
Yeah, definitely. Thanks. Vivek, sorry, we've been taking off your doctor.
No, this wonderful discussion is really productive and high quality time that we are spending. So so multiple things. So first, I think we already discussed a lot of aspects in our discussions, but I think this would be more of like a summarization of that set. So one thing I would say would be the data hygiene. Spend more efforts on that data foundation layer, because to me that's a less celebrated but the most important layer based on which everything else is built. So I have seen enterprises stressing or advertising on the AI strategy which they are taking. But I think they have to give equal. I mean, they may be giving equal importance, but they may not be advertising it as prominent for the AI. But that data hygiene, data standardization, data integration part, that would be something which it's not just one single enterprise, any enterprise for that matter, of any scale. Doesn't matter if it's like a Fortune 500 company or a startup. The earlier, the better. Like when you get into that data hygiene principles, then everything you build on top of that would be of high quality. So that's one thing. And second thing is regarding the AI governance itself, especially with this AI democratization that's happening now, right? With even people without much formal knowledge about AI, they are able to use AI, which is a good thing. I'm not saying that's a bad thing. That's really a good thing because AI is getting into the hands of people and they're able to consume that. But that needs to be done cautiously, because building something that works doesn't mean that's a good solution. And if you know, so the important point is that the important point is not about making something work. It's about, if that something breaks, do you know how to fix that? That's where the distinction comes between a raw usage of AI and responsible usage of AI. So no coding agent or vibe coding is going to come in your way and give you the answer for that. So that governance is something which you need to build. So I would say, or maybe I can call it as an AI hygiene. So data hygiene and AI hygiene, these would be the two things that any enterprise needs to give more importance to. Just because people can build AI using vibe coding tools, maybe that may not be like a down the line. The return would be, it would be a negative impact if you don't do that responsibly. And think of a situation where 1,000 different people build 1,000 different AI solutions on a unhygiene data. You are just the problem is getting multiplicatively bad. So start from the first principles, have a good data hygiene, uh, democratize AI, but in a very responsible way with AI hygiene. So in that way, I think that's the way to go for responsible AI. Yeah, absolutely. Again, thanks for having me here. Thank you, Vivek and Joshua, for all the wonderful questions. Yeah,
Thanks, Karthik.
I was
It's a
really
good
a
discussion. Yeah, thanks.
sure. See you then. Bye.